Definitely we're gonna have class that day. Today we're gonna keep going with Lewis structure and then go to the VSPER theory. So let's start with an eye picker. Okay. So what is the Lewis structure of NO2 plus? And I'm gonna stop it at 2 minutes. So again, you have the rules. You have this sheet in there. If you don't have it, I have some more in here. Come down there, grab one. Okay, so I'm going to stop it right here and check what you have. And I have B as 86%. B is the right answer. So first of all, the first thing that you should do whenever you're asked to write down the Lewis structure is find out the central atom. And we're gonna stop talking. Okay? So first, the central atom. The central atom should be the atom with the lowest electronegativity. We know that the electronegativity increases this way and this way as we go in the periodic table. Nitrogen is less electronegative than oxygen, so nitrogen is the central atom. And the two oxygen are the terminal one. Now the total number of valence electrons, nitrogen belongs to group 5A, so it's going to have 5 electrons. And I have 2 oxygens, each belongs definitely to the same group, which is 6. And I have a plus in there. That means this whole polycation lost 1 electron. So I'm going to put minus 1 electron, because a plus means a cation, that means lost 1 electron. So I'm going to have total of 16 electrons. Now I'm going to take those electrons that are in bonding into consideration. So I have 2 bonds, 1. So each bond corresponds to 2 electrons. 1, 2, 3, 4, minus 4 electrons. I have 12 electrons. Now those 12 electrons, I'm going to put them on the terminal atom until it satisfies the octet rule. So 1, 2, 3, 4, 5, 6. 7, 8, 9, 10, 11, 12. Then I'm going to look to the nitrogen. The nitrogen only have 1, 2, 3, 4. Those oxygen have the octet rule. So what I'm going to do, I'm going to borrow those 2 electrons from this oxygen and those oxygen. And I'm going to end up with this structure. So if I stop here, that's the wrong Lewis structure. Because This is not the right one. The right one is with a bracket plus, because without that plus, that wouldn't be the structure. So anytime I give you a polycation, a plus or a minus, you need to write those two brackets and the plus or a minus. Otherwise, if I just put N double O, double bond O without the bracket plus, that's the wrong representation of the Lewis structure. Okay? So now we're gonna start with another algorithm. Okay, so which of the following is the correct Lewis structure of OH minus, which is hydroxide, which you're gonna hear a lot about later on in Chem 112. And I'm gonna stop it at 150. I'm gonna stop the algorithm at 150. Okay, so I'm gonna stop it right here and check what he's saying. And I have 86% for C. C is the right answer. Again, the same rules. What is the central atom? In this case, I have two atoms, so there isn't a big choice. And anyway, hydrogen is terminal. So I'm going to put oxygen and I'm going to connect it to the hydrogen. Oxygen, the total number of valence electrons. Oxygen belongs to group 6, so that means it has 6 electrons. The hydrogen belongs to group 1, so the number of valence electrons is 1. And it is OH minus, that means it gained 1 electron. So I'm going to add this because it is OH minus. So the total is 8 electrons. I should take those electrons in bonding into consideration. I have 1 bond minus 2 electrons because each bond corresponds to 2 electrons. So in bonding, so the total is 6 electrons. I'm going to put those 6 electrons as lone pairs on the terminal atom. In this case, there is no terminal atom. We said that hydrogen does not obey the octet rule. All what it needs are 2 electrons, and there are 2 electrons for the hydrogen, so I'm going to put them on the oxygen. And that structure is not complete until I put a bracket minus. If I don't do that, that's wrong. Okay, let's do some more on this structure. And this time I'm going to stop it at 120. So I'm going to stop it right here and check what you think. And I have 88% for CC is the right answer. So again, the central atom should be which is the one that has the lowest electronegativity. In this case, hydrogen is definitely less electronegative than oxygen, but in this case, hydrogen can never be the central atom. It's always a terminal atom. This is why I'm going to put oxygen as the central atom, although it is higher in electronegativity, because hydrogen can never be a central atom. Now, the total number of valence electron. I have 3 hydrogen that belongs to group 1, so they have definitely, each has 1 electron, plus oxygen belongs to group 6, so it has 6 valence electron, and I have a plus, that means minus 1 electron. That's total of 8 electrons. I have 1, 2, 3 bonds, each bond 2 electrons, minus 6 electrons in bonding. So I'm left with 2 electrons. The hydrogen cannot accommodate lone pairs, so I'm going to put it on the central atom, and this is not complete until I put a bracket plus. Okay, so let's do some more of this under this structure. Again, I'm going to stop it at 120. Okay, so let's stop it right here and check what you think. And I have C at the highest, which we shall see if C is the right answer. So, first of all, so I have nitrogen gonna be the central atom because it's the one with the lowest electronegativity. And in total, I have 3 oxygen. They belongs to group 6. Plus I have nitrogen belongs to group 5, and minus NO3 minus, that means plus 1 electron. That's total of 24 electrons. I have minus 6 electrons in bonding, 1, 2, 3, 4, 5, 6. So I end up with 18 electrons. I'm going to put the lone pair, the 18 lone pair, electrons in lone pair on the oxygen, so each gonna accommodate 6 times 3, 18 on the oxygen. Then I look to all the oxygen have the octet rule, but the nitrogen does not. So I'm gonna follow one of the lone pairs into the bonding. And with a minus. And that's definitely make the C the right answer. Okay. Let's see see what's next. Okay. We're gonna talk more about the nitrate when we're gonna talk about resonance, about more structure, more Lewis structure when we talk about the resonance. But for the moment, with the information that we already learned for the moment, that's one of the right structure, is the correct Lewis structure. Now how are we going to write the Lewis structure of something like HNO3, which is considered an oxo acid? And by definition, oxo acids are the acids that have oxygen in them. For example, HCl, we learned in chapter 2 that it is an acid, but it isn't an oxo acid. Why? Because it doesn't have an oxygen. While, for example, H2SO4 is an oxo acid. H3PO4 is an oxo acid. Why? Because it has oxygen. And so on. Any acid that has an oxygen, one or many oxygen, it is an oxo acid. HCl, HBr, they aren't oxo acids. Now, the special about those acids, when we're writing the Lewis structure, for the Lewis structure to be right, you have to connect the hydrogen to the oxygen, not to the central atom, not to the nitrogen, not to any other thing. It should be connected to the oxygen. Otherwise, even the other Lewis structure that you're gonna write is gonna be, it's gonna look right, but it's not. So this is why we're gonna deal with the acids alone. So the way that I'm gonna do that is nitrogen gonna be the central atom because the one is the one with the lowest electronegativity. Hydrogen is less electronegative than nitrogen, but it cannot be a central atom. This is why I'm gonna put the nitrogen as the central, and I'm gonna put the 3 oxygen connected to the nitrogen. And since it is an oxo acid, I have either a choice to add the hydrogen to the nitrogen or to the oxygen. If it is an oxo acid, connected to the oxygen, not to the nitrogen. Okay? That's a rule of thumb. The same for phosphoric acid, connect the hydrogen to the oxygen, not to the phosphorus. The same for any other oxo acid that we're gonna learn about today. Okay? Now after that, I can do exactly the same. After I connected the structure, I'll do the total number of electrons. I have 3 times 6, I have 3 oxygens. They belong to group 6. I have 1 hydrogen, and I have, so that's total of 24 electrons. Okay, I have 1, 2, 3, 4 bonds, 4 times 2 because each bonds correspond to 2 electrons, so minus 8. So I end up with 16 electrons. Then I'm going to put those 16 electrons on the terminal atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12, 13, 14. Okay? Then I'm going to look exactly as we did before. We're going to look to each atom in there if it has the octet rule or not. So I know that the nitrogen needs more, so I'm going to borrow either from this or from this oxygen or from this oxygen, 2 lone pair to the and that's the structure of HNO3, which is an oxo acid. Okay, so let's do an eye clicker about the acids. And by the way, there is one thing, you can borrow either those 2 lone pairs or those 2 lone pairs. Rarely, if ever, you don't borrow those lone pairs for the oxygen that is connected to the hydrogen. Don't do that. Just borrow the lone pairs of the oxygen that are not connected to anything else. We're going to learn more about it when we talk about the formal charge, that this is the better representation of the Lewis structure. Okay? So borrow those lone pairs either from this oxygen or this oxygen. It doesn't matter which one of them you choose. And this is, we're going to learn that they are equal when we talk about resonance structure later on in this chapter. Okay, so let's do an eye clicker. Write the Lewis structure of H3PO4. I gave you two structures and to choose one of them. And I'm going to stop it at 120 so that you get the chance to really write the Lewis structure instead of just eliminating one choice over the other in this case. Okay, so I'm going to stop it right here and check your answers. And I have 97% for B. Yes, B is the right answer for one good reason. Now in here it's only two choices. Definitely in the exam it's going to be 5, so you have to get to the Lewis structure step by step. This is totally wrong because first of all the hydrogen, first it is an oxo acid. Clearly it is phosphoric acid is an oxo acid. So the hydrogen, as I said, each hydrogen of the oxo acid should be connected to an oxygen. In this case, the hydrogen is connected to the phosphorus, and this is why it's going to be wrong Lewis structure. In other words, when you're dealing with those, the first thing is to connect those right. And the first thing that should come to your mind is the following. The central atom, in this case, phosphorus is the central atom compared to the oxygen. So you're going to connect it to the oxygens, to the 4 oxygens. Then the hydrogen, you connect each hydrogen that you have to the oxygens, not to the phosphorus, not to anything else, just to the oxygens. And from there, you do exactly the same, the total number of electrons, the one in bonding, then put the lone pairs on the terminal atom, then borrow electrons. And if you want to borrow electrons, don't borrow them from this oxygen or this, borrow them from, in this case, only this oxygen. Okay, and this applies to any oxo acid out there. Okay. Now, in all of these cases that we talked about, all the elements except hydrogen that we saw, they obey the octet rule. All of them. All what we talked about, we didn't see even one example that the atom does not obey the octet rule. And now, today, we're going to talk about those elements that has an expanded valence shell. In other words, some elements going to have 10 electrons around them, 12 electrons around them. And those are from group 3, from period 3 and on. All of these can make expanded valence shell. That means they can have 12 electrons around them. They can have 10 electrons around them. And the reason behind that is all of these have an MTD shell that they can use it to make those excess, for example, 2 bonds more. So in other words, you're going to see atoms, only those. Carbon can never do more than 4 bonds. Nitrogen can never do more than have 8 electrons around it. It's only those elements from period 3 on. They can do that because they have a D shell, an empty D shell, that they can use that shell to make more bonds around them. Definitely, I'm going to show you examples. We call those compounds that have more than, the central atom has more than 4 bonds, 8 electrons, we call them hypervalent compounds. They contain an atom with more atoms attached to it than is permitted by the octet rule. We call them hypervalent. An example of that is PF5, phosphorus 5. That doesn't mean that they don't obey the octet rule. Sometimes they do, sometimes they don't. So you're going to see some compounds where phosphorus has more than the octet rule, and sometimes they have just the octet rule. So how are you going to deal with that? One of the hypervalent compounds is PF5 that I'm going to show you how to draw the Lewis structure for it. So PF5, the total number first, I'm going to put the phosphorus because it's lower in electronegativity as a central atom, and I'm going to connect it to the terminal ones, which is clearly 5 fluorines. So already I'm saying that the phosphorus has 10 electrons around it. It doesn't have even 8 electrons at the octet rule. And this is the case. Why? Because phosphorus is from period 3 on. Now the end total, I have 5 fluorines, they belongs to group 7, plus phosphorus. Phosphorus belongs to group 5, so that's 40 electrons. And I have 1, 2, 3, 4, 5 bonds, each 2 electrons, minus 10 electrons. So that's a total of 30. This is in bonding. Now each fluorine, I'm going to put those 30 electrons as lone pairs on fluorine. I know that each fluorine can accommodate 6 electrons. 6 times 5, that means that's 30 electrons. So as you can see, everything is exactly as we did before. The only thing that is different is your knowledge that this phosphorus, yes, it is from period 3 on, it can accommodate, we can draw 5 bonds to it. Definitely if you see 5 bonds to oxygen, that's not right. 5 bonds to carbon, that's definitely wrong. If you see fluorine doing 6 bonds, 5 bonds, that's definitely wrong. It only applies from period 3 and on. Okay? Now another example of hypervalent is sulfur F6. So what about you take 1 minute and write the Lewis structure of SF6? Okay. So the first thing is to determine the central atom. Sulfur is lower in electronegativity than fluorine. It's well known that fluorine is the most electronegative out there in the periodic tables. So I'm going to put the sulfur and connect it to the terminal atoms, which is already 6. 1, 2, 3, 4, 5, 6. Total number of valence electron, I have sulfur, it belongs to group 6. And I have 6 fluorines, they belong to group 7. So that's total of 48 electrons. I have 6 bonds times 2, each bond corresponds to 2 electrons, minus 12 electrons in bonding. So I end up with 36 electrons. I'm going to put 6 electrons on each fluorine. So that's going to end up to 36 electrons. And that would be the Lewis structure of SF6. Okay? Now more of the Lewis structure of hypervalent compounds is summarized in the upcoming table. You have almost all what you're going to see in this course as Lewis structure of hypervalent. It's already there the same. We treat anion the same way. If it is minus, we add 1 electron. If it is If it is a plus, you make -1 electrons. If I'm you, I'll take only the compounds without looking to the Lewis structure and try to draw them. I can make them eye clicker, but that's gonna take another one lecture to do that. So you have already the answers for each. If I'm you, I'll practice just doing that, writing down the Lewis structure of all of these hypervalent. Okay? The only weird thing that you're gonna see that we never talked about is those two compounds in here. Xenon, which belongs to group 8A, which is the noble gases. We said that this group, they don't react because they have the octet rule. This is the only, actually there is one more, which is xenon outside. Xenon is the only noble gas that react and make reaction, and that was discovered by kind of a chance that a professor had xenon and F2 in a bottle in his office, and suddenly he saw a precipitate, and this is the only exception of a group 8A, and these are the 3 examples out there. So this is mainly the only one you may see and say, oh, that's weird. She said that group 8A, they don't react. This is one of the examples. Those 3 are the examples where xenon, which is a noble gas, reacts. And definitely form compounds. So we talked about elements from period 3 on that they exceed the octet rule. Now we're going to talk about those elements that they don't have. They have incomplete octet rule. And definitely all of you know about hydrogen. We've been working with hydrogen. It only needs 1 bond, 2 electrons. So it doesn't have an incomplete octet. Another example is beryllium. It usually just needs 4 electrons. It doesn't have the octet rule. So if you see beryllium F2, beryllium Cl2, that's normal because beryllium would have only 4 electrons around it. It has an incomplete octet rule. BF3 is also boron, has usually only 6 electrons. It has incomplete one. There are examples where you can see boron with 4 bonds. That means the octet rule. There is 1 or 2 examples of that. So boron can either be in the incomplete octet or the complete octet. An example of the incomplete octet is being BF3, BCl3, BI3. And there is another example where it can have the octet. It can obey the octet rule. So by this, we kind of covered all those kind of stuff that are exceptions, like oxo acids, where we are obliged to connect the hydrogen to the oxygen, the expanded rule, octet rule, the incomplete rule. So all these are all the cases that are out there. So from now on, you need to practice more. You have this worksheet. I'm gonna upload the key today for this worksheet. You can, for the moment, you can only draw the Lewis structure. This is gonna be so helpful. It has all these different kinds of Lewis structure. So I advise you and I encourage you to do this worksheet. Now, what we're gonna start with is now we know that how to draw the Lewis structure. Our next step is to know the geometry. Now, in all the cases that we had before on drawing, for example, I'm gonna take an example, methane. I draw methane like this. And I want on the screen. But does methane exist as on the screen flat? Do I have the methane, like if I have a methane molecule, does it have carbon, hydrogen, hydrogen, hydrogen connected to it on this plane? No, everybody is saying no, that's not right. In real life, methane looks like this. This is the real methane, not on the plane of this paper as we're drawing it. And today we're gonna learn why and how to figure out the structure of any Lewis structure. So we're gonna take it from 1 dimension to the 3D. This is what we're gonna do today. Now, but why do you think that methane gonna have this structure? Not any other structure. Why this? What is obliging it to go to this structure? Very good. She's saying the electrons in the bond. She's saying don't forget that the electrons in here they have the same charge, and they don't want to be close to each other. Those electrons in bonding here and here and here, they don't want to be close to each other. They repel each other. And this is what the VSPER theory out there says. And it stands for valence shell electron pair repulsion. So anything that we're going to see today as structures, it's going to be due to the repulsion. And this is the distance. This angle here is 109.5. And that's the best distance so that the electron kind of has the lowest repulsion between each other. And this is why methane has this tetrahedral structure. So mainly VSPER theory is based on the idea that those bonds are electrons and they're going to repel each other and they prefer to be far away from each other. And this is what we're going to follow up with today with VSPER. So first, the shape of the molecule can be predicted using the valence shell electron pair repulsion. From now on, I'm going to refer to it as VSPER because it's easier to say it this way. And definitely, I will going to tell you, use VSPER model to predict the geometry. As I said, the model states that electrons in bonding should be as far as possible from each other, and this is what determines the structure. So what I'm going to do now, I think everybody has either the blue or this kind of pale lilac color. And so I'm gonna walk you through this table, although it's there. I'm gonna walk you through this table. Then we're gonna do some eye clicker to predict the structure of the geometry of molecules. Again, the way that we're gonna do it, first we're gonna figure out the Lewis structure. Then the second thing will be using the VSPER theory. Now, in this table, the first I'm going to have an example, that means a chemical symbol. I mean by that the VSPER symbol. We're going to talk in a minute what is A, what is X, and the geometry is, what's that geometry? And the angle is the angle between the bonds, okay? Here when I say angle in degrees, and all of them are in degrees, I'm talking about the angle between the two bonds. Now, A in this VSPER represents the central atom. So let's say I have BeF2, and I'm going to insert it here. If I have BeF2, so we just draw the Lewis structure of that minutes ago, which is this. A represents the central atom, which is B. X represents the terminal atoms. So I have two terminals atom connected to the central atom, which is A. I have 0 lone pairs on the central atom. I'm talking about the lone pairs on the central atom. I have 0 lone pairs on the central atom. E represents the lone pairs on the central atom. In this case, in the BeF2, I have 0 lone pairs on the central atom. So the structure, the VSPER model is AX2. Because E0 does mean there is no lone pair. So A represents the central atom in the Lewis structure. Definitely first you need to draw the Lewis structure, the central atom. X, the terminal atoms definitely connected to the central. E, the lone pair electrons on the central atom, and that's very important, not on the terminal atom, on the central atom. Let me just highlight central atom. Okay? So, now from that, I know that the VSPER model for BeF2 is AX2. Now, for any Lewis structure that you figure out that after drawing the Lewis structure, you figure out that it ends up being a VSPER model of AX2, the structure gonna be linear. Why? Because this is the best angle so that the two bonds are far away from each other. So any AX2, any Lewis structure that you translate it to AX2, it's going to be linear. The angle between the two bonds is going to be 180. And by the way, you need to learn those. That means you'll not be given this table in the exam. This table is just to help you, I summarize it to help you learn those, but it's not going to be given to you in the exam. You need to know what is the symbol, what is the shape or the linear, whether it is linear, tetrahedral, and you need to know the angle. You need to know all three of those, all four information of those. Now let's go to the next example, which is BF3. So what I'm going to do, I'm going to insert again. So BF3, so I know that this is the Lewis structure of BF3. So B, A represents the central atom, which is boron. It has 3 terminal atoms, so it's going to be AX3, and I have 0 lone pairs on the central atom. So the VSPER symbol for this Lewis structure is AX3. And any atom that has AX3 as a VSPER symbol, the best arrangement so that the bonds are far away from each other with the least repulsion is this shape, which is trigonal planar, where the angle between the bonds, this angle in here, which is right there, is 120 degrees. Okay, and this is the case for any Lewis structure that's going to end up with AX3. Okay, now let's go to the methane as an example. So the Lewis structure of methane is CH4. Now definitely I'm going through the Lewis structure faster now, but definitely you need to determine the central atom connected to the terminal, calculate the total number of valence electron minus the bonding, put the lone pairs on the terminal atoms. So the central is AX4. So for the symbol AX4, the best arrangement is what we showed you before, what I just showed you before, which is the tetrahedral. So the structure is tetrahedral, and the angle is 109 between those bonds is 109.5. So the angle between all of these is 109.5. Okay, so that's for AX4. Now let's go to NH3. For NH3, the Lewis structure, if you go step by step, this is the Lewis structure of NH3. So nitrogen is a central atom. It has 3 terminal and 1 lone pair. So it's going to be AX3E. This is the VSPER model for that. In other words, if we look at it, it is mainly AX4 as if it has 4 bonds, and then we have a lone pair. So what's going to happen that the lone pair gonna take the place of 1 bond. So in here you have a lone pair in there, and usually the lone pair pushes the bonds more down than a bond. So what you have is the electrons right here, and then you have those 3 bonds. So mainly it came from the tetrahedral, but instead of this bond, you have the lone pairs on there that they are pushing down those. So the structure of this is trigonal pyramidal, which you can see in here. So AX3E, the structure is trigonal pyramidal. The angle is even smaller than the tetrahedral. Why? Because the lone pairs that you can't see in here, but they are there, they push more the bonds down, which makes this angle smaller than a tetrahedral. So the angle in this case, 107.5. Definitely the pyramidal is different than the trigonal planar. Okay? The trigonal planar, the angle is 120. All of them are on the same plane, while the trigonal pyramidal, as you can see, is different. Because sometimes what some students do is just you look at AX3 and AX3E as both of them, okay, why they don't look the same? Because you have a lone pair in this case, while there is no lone pair in that case. This is in the same plane. Those is pyramidal in here. So now let's go back to this one. So in this case, we call this AX3 is the geometry of the molecule. The geometry of the molecule is trigonal pyramidal, and its electron geometry, we call this electron geometry or lone pair geometry. I think I will call it lone pair geometry. So in the case of lone pairs, you have to think where it is coming from. In other words, 3 terminal plus 1, that's AX4. So the electron geometry of ammonia is tetrahedral, yet the geometry of the molecule is trigonal pyramidal. So what does that mean? So the electron geometry or the lone pair geometry is telling you, oh, what if you can see those lone pairs that are there? What is going to look like? If we can see them residing there, it's going to look like tetrahedral. But if you look to the molecule at any point, it's going to look like pyramidal because you can see those lone pairs. This is the difference between the electron geometry, lone pair geometry, and the molecular geometry. So the molecular geometry is the way you're seeing it without the lone pair, without you being able to see the lone pair in there. Okay? So let's go one further on there. What about the water? Let's check water. So this is the Lewis structure of water that we did earlier. So its VSPER model is AX2E2. We have 2 lone pairs residing on the central atom, 2 terminal 1. So it's AX2A. So mainly, if we look at it, it's coming 2 plus 2. So it's coming from AX4, from the tetrahedron. Now, I'm going to remove one. There is a lone pair in here that we can't see. I'm going to remove this bond because there is a lone pair. So you end up with a bent. We call this a bent structure. And this is the structure of any atom with the Lewis structure that gives you AX2E2 as a VSPER model. So bent, the angle is 104.5. And it is smaller than that of 107 of the pyramidal. Why? Because now you have lone pairs, and as I said, the lone pairs kind of repel more the bond, and this makes this angle smaller than the trigonal pyramidal or than the tetrahedral. So mainly, as you can see, all of those that are coming from AX4, the angle is close enough. It's 109, 107, 104.5. Okay? Now this is for the water one. Now, let's go to the next one on your table, on the table that you have. Now we're going to go to Pppffffffffahhhhh, which clearly is a hypervalent compound that we just talked about minutes ago, and we showed the structure of that. So again, for this one, it is AX5, and it is trigonal bipyramidal, and it's right here. So it's trigonal bipyramidal, and it's called the trigonal bipyramidal because it has a triangle in the equatorial, and it has 2 on the axial. And we're going to talk more about AX5 on Friday. So just remember that today is a Monday scheduled on a Wednesday, so double check your labs. And don't forget to go to the lab if you have a lab today.